Good afternoon, ladies and gentlemen. Can everybody hear me? How are you guys doing? I'm also doing okay, thank you. So, for today's lecture, we are going to talk about neutron stars, black holes, and other compact objects. So, before I start, do you guys know what a neutron star is? So, that we talk about. So, in a previous lecture, we learned about the Chandrasekhar limit. So what happens if we take degenerate matter and add more degenerate matter to it? So before we get to a black hole and the other cool stuff, we have done this first part. So a average type star that becomes a red giant, then a planetary nebula, and then ends as a white dwarf. If we have a massive star, it becomes a super red giant, a supernova, and then, depending on how much mass it has, it will either become a neutron star or a black hole. So, for this lecture, we will look at how theory predicts the existence of neutron stars, how did astronomers actually discover neutron stars, and how does the theory predict the existence of black holes? And how do astronomers know that black holes actually exist? So, who of you has viewed the one of my old previous lecture recordings on this lecture I'm about to give that I uploaded yesterday? Okay, cool. So this will be the same lecture. But before we begin, let me show you an overview of what a neutron star is.
When a solar mass star ends its life, it does so with a bang, a supernova. And when it's all over, there's a couple of octillion tons of superheated plasma expanding away from the explosion site at a fraction of the speed of light, a whole mess of energy released in the form of light and neutrinos, and a bizarre little ball of quantum nastiness in the center, composed almost entirely of neutrons. The properties of this neutron star are almost as bizarre as things get in the universe. And if it all seems rather alien to you, well, that's okay. For a little while, astronomers wondered if aliens really were behind what they were seeing. No, I'm not saying aliens. When we last left the core of a high-mass star, it was in a bad way. Milliseconds ago, it was fusing silicon into iron, but now it's collapsing under its own immensely powerful gravity. The collapse takes a fraction of a second, but a lot happens in that fraction of a second. In lower mass stars, the core supports itself via electron degeneracy pressure, the result of a rule in quantum mechanics that says electrons vehemently resist being squeezed together. But even electron degeneracy fails to stop the collapse if the core has a mass more than about 1.4 times the mass of the sun. That's just too much of a load to bear, and the collapse continues. Under these huge pressures, a funny thing happens. Protons, electrons, and other subatomic particles get smashed together, and they merge to form neutrons. And this happens to almost all of them. When the core collapses down to about 20 kilometers in diameter, it's essentially a ball of neutrons with some protons and electrons here and there that survived, and a crust of normal but highly compressed matter on top. When this happens, yet another effect comes into play. Neutron degeneracy. Like electrons, neutrons resist being squeezed too tightly together, but this time the strength of the pressure is far, far stronger than for electrons. If the core is less than about 2.8 times the sun's mass, the collapse runs into a wall. It stops. This generates a huge shock wave, which, along with a flood of energetic subatomic particles called neutrinos, blasts outwards, blowing up the star. What's left of the core after the metaphorical smoke clears is a neutron star, one of the most bizarre objects in the universe. Such a star would be extremely weird, or really just extreme. Its mass would be more than that of the entire sun, all packed into a sphere maybe 20 kilometers across. Now, let's just stop there for a sec and let that sink in. The sun has a mass 300,000 times the Earth. Imagine packing that all into a ball the size of a small city. Too mind-boggling? Okay, think of it this way. You are mostly empty space. Every atom in your body has a nucleus made of tightly packed neutrons and protons, and electrons whizzing around outside them. If you could magnify an atom to be 100 meters across, the nucleus would be roughly the size of a marble. Imagine all that empty space between the nucleus and the electrons. That's a normal atom. But in a neutron star, all of that space would be filled with neutrons. All of it. Every nook and cranny inside the neutron star has matter in it, all the way down to the scale of an atomic nucleus. This is what gives a neutron star its mind. I'm now going to barrage you with very large numbers. So take a deep breath and you might want to sit down. Neutron stars are ridiculously dense. A single cubic centimeter of neutronium, as neutron star stuff is usually called, has a mass of about 400 million tons. Want some perspective on that number? Well, very roughly, that's the total mass of every single car and truck in the United States. Imagine a couple of 100 million vehicles crushed down until they could all fit inside this six-sided die. That's neutronium. It's so dense that, as far as it's concerned, normal matter is a slightly polluted vacuum. If you set it on the ground, it would fall right through the Earth. Now, anything that dense has a huge gravitational pull. If you were on the surface of a neutron star, well, you'd be very dead, obviously, like immediately, flattened down to a thickness of just a few atoms. And that's because a typical neutron star has a surface gravity 100 billion times stronger than Earth's. I have a mass of about 77 kilos, and here on Earth I weigh about 170 pounds. On a neutron star, I'd weigh 17 trillion pounds. That's 23,000 times the weight of the Empire State Building. But wait! There's more. In our introduction to the solar system, I mentioned that when you take a spinning object and shrink it, the spin will increase. The usual example is an ice skater drawing in his arms, increasing his rotation until he's a blur. The same is true for the star's core when it collapses into a neutron star. It may have had a very slow spin before the supernova, maybe even taking weeks to spin once. But when it shrinks down to just 20 kilometers across and becomes a neutron star, that rotation will increase by a huge factor. A freshly minted neutron star might spin several times per second. The magnetic field increases as well. A star like the sun has an overall magnetic strength not too different from the Earth's, but when that core collapses, the strength of the field skyrockets, and a neutron star can easily have a magnetic field several trillion times stronger than the sun's. That's strong enough to erase your credit card from 100,000 kilometers away. See? Ridiculous. All of these properties are brain-melting. But are they real? Could an object like this really exist? Oh my, yes. The first neutron star was detected in 1965, though not recognized for what it was at the time. A couple of years later, another one was found, and this time was correctly identified as a neutron star. But then things got weird. In 1967, Jocelyn Bell was a graduate student helping build a radio telescope. There was a persistent noise in their data they couldn't seem to fix. Bell studied it night after night, finally figuring out that the pattern wasn't a problem with their data. It was from an actual astronomical object. She had discovered the first known pulsar. What's a pulsar, you ask? Pulsars are neutron stars. In a nutshell, their rapid rotation, coupled with their incredibly strong magnetic fields, launch twin beams of energy away from the star, like the beams from a lighthouse. The beams sweep around as the star rotates, and from Earth, we see this as a pulse, a blip of increased brightness. This pulse can be detected in visible light, radio waves, and even X-rays. The spin of a neutron star is amazingly stable, making these pulses act like a very accurately timed cosmic clock. In 1967, no one could believe a natural object could do this, and this object was half-jokingly given the name LGM-1, Little Green Men 1. Now we know of over 1,000 pulsars in just our galaxy alone, And we know they're the leftover cores of massive stars that exploded. Some spin with periods many seconds or even minutes long. Some are in binary systems. Another normal star orbits them. If they're close enough together, the neutron star can rip material off the other star and feed on it. This increases the pulsar's spin, and we know of a few that have incredibly rapid rotation rates. Some spin hundreds of times per second. These are called millisecond pulsars, and if they spun much faster, the centrifugal force would rip them apart despite their tremendous gravity. Even after 1,000 years, a pulsar can still be a force to reckon with. There's a pulsar in the center of the Crab Nebula, the remains of a star that exploded to create that supernova remnant. A substantial fraction of the light emitted from the nebula is powered by the pulsar itself. Its fierce output energizes the nebula, causing it to glow brightly even after a millennium. I'm telling you, thinking about neutron stars makes the hair on the back of my neck stand up. And I haven't even mentioned magnetars yet. Neutron stars are more than just weird little balls of neutrons. They have a crust, probably a few centimeters thick, made of highly compressed but more or less normal matter, squeezed into a kind of highly stiffened crystal state. The magnetic field of the star penetrates this crystalline crust and stretches out for quite a distance. In some neutron stars, the magnetic field is even stronger than usual and can be, get this, a quadrillion times stronger than the sun's. These uber-powerful neutron stars are given the name magnetars. They're relatively rare. Maybe 10% of all neutron stars are born as magnetars, and they have short lifetimes. The magnetic field is so strong it acts like the brakes on a car, slowing the neutron star's spin. That spin helps power the magnetic field, so the field weakens as the star slows. But while they're around, magnetars are the most magnetic objects in the universe. And with great power comes great responsibility. If your responsibility is to be one of the scariest objects in the universe. Why? In a neutron star, the crust and magnetic field are locked together, so a change in one affects the other. The crust of the star is under incredible strain due to the intense gravity and rapid rotation. If the structure slips, it can snap, creating a starquake, like an earthquake, but just a wee bit stronger. In an earthquake, huge amounts of energy are released when the Earth's crust shifts and snaps, enough to destroy buildings and quite literally move mountains. But in a neutron star, this effect is multiplied hugely. Remember, the crust is phenomenally dense and the gravity is enormous. If the crust strains and snaps, dropping just a single centimeter, the resulting release of energy is vast beyond imagining. This energy is released as a tremendous explosion in the crust, shaking it. This also shakes the magnetic field, which reacts poorly. When the sun's magnetic field throws a tantrum, we get a solar flare, which can be as powerful as billions of nuclear bombs. A magnetar flare dwarfs that into insignificance. It can be trillions of times stronger than a solar flare. In a fraction of a second, a magnetar can release as much energy as the sun gives off in 250,000 years. In 2004, astronomers were stunned when a huge blast of X-rays slammed into orbiting satellites. One of these satellites, named Swift, actually had its detectors saturated with X-rays, even though it wasn't even pointing at the source at the time. The X-rays literally came right through the side of the satellite with such intensity that Swift, which was designed to detect powerful X-ray sources, was momentarily blinded by them. The source of this X-ray burst was quickly determined to be a magnetar called SGR 1806-20, and the effects were incredible. It actually compressed the Earth's magnetic field and partially ionized the Earth's upper atmosphere. Oh, did I mention that this magnetar is 50,000 light years away? That's halfway across the galaxy. That's incredible. At a distance of 500 quadrillion kilometers, its effects were felt more strongly than a powerful flare from the sun. The good news is that there are very few magnetars like this in the galaxy. Probably fewer than a dozen. Also, catastrophic explosions like the one in 2004 are rare. If one had happened any other time in the past 40 years or so, we would have detected it. And frankly, it's really cool that we had astronomical satellites orbiting the Earth which could study it. We've come a long way in understanding neutron stars since they were first discovered, but there's much about them we don't understand. Every time we find out more, we find out they're even weirder than we first thought. And yet, for all that, they're not the weirdest things in the sky. Not by a long shot. That place is held pretty securely by the other type of object created in a supernova, a black hole. Stay tuned. Today you learned that when a
So hopefully that gives us an overview of neutron stars, which is very cool. So, did you guys realize that objects such as neutron stars can exist? Ah, so that is what. So we will learn a bit more about that, and then go on to black holes. So depending on how much mass the star has, at the end of its life, it will either end up as a neutron star or end up as a black hole. So a neutron star containing little over one solar mass compressed to the radius of 10 kilometers can be produced by type 2 supernovae. And for example, a white dwarf has about the same mass but is about the size of Earth. A neutron star's density is so high that physicists calculate this material is stable only as a fluid of neutrons. Theory predicts that such an object would spin a number of times a second, be nearly as hot at its surface as the inside of the sun, and have a magnetic field trillions of times stronger than Earth's. And two questions should occur from this. The first one is, how could any theory predict such a bizarre object? And second, do neutron stars really exist? So neutrons were discovered in a laboratory in February 1932. Only 2 years later, in January 1934, Caltech astronomers Walter Baade and Fritz Zwicky published a seminal paper. They showed that some novae in historical records were much more luminous than the rest and suggested that these were caused by the collapse of a massive star's core, resulting in an explosion they named a supernova. The core of the star, they proposed, would form a small and tremendously dense sphere of neutrons, and Zwicky coined the term a neutron star. Over the following years, scientists applied principles of quantum mechanics to see if such an object was indeed possible. Neutrons spin in the same way that electrons do, which means that neutrons must obey the Pauli exclusion principle. In other words, if neutrons are packed together tightly enough, they can become degenerate just as electrons do. White dwarfs are supported by degenerate electrons, and quantum mechanics predicts that even denser mass of neutrinos could support itself, neutrons could support itself by the pressure of degenerate neutrons. So how does the core of a collapsing star become a mass of neutrinos? Nuclear physics provide an explanation. As the supernova begins, the core collapses inward. If the collapsing core is more massive than the Chandrasekhar limit of 1.4 solar masses, then it cannot reach the stability as a white dwarf because the weight is too great to be supported by degenerate electrons. The collapse of the core continues, and the atomic nuclei are broken apart by gamma rays. Almost instantly, the increase in density forces the freed protons to combine with electrons and become neutrons by this reaction. So this is just the equation of what is happening. You don't need to know this equation. This is only for background information. So as a result of the production of each neutrino, or neutron n, and neutrino nu, you learned in a previous chapter that a burst of neutrinos n during supernova explosion helps blast the envelope of the star away, and the star's core is left behind as a neutron star. So when we look at these different stars, where do you think the separation line is between a white dwarf and a neutron star? Any idea? So any star greater than 8 solar masses, between 8 and 20 solar masses, will become a neutron star. So which type star is our own sun? So our own star is a G-type star, which is 1 solar mass. So above an F-type, so usually from about an A-type star that we have here, we get a neutron. And if it's above 20 solar masses, then we get a black hole. So as you learned in the previous chapter, a star that begins its life with less than about 8 solar masses can lose enough mass to die by forming a planetary nebula and then leave behind a white dwarf. More massive stars also lose mass rapidly, but model calculations indicate they cannot shed mass fast enough to reduce their mass below the Chandrasekhar limit. So it seems likely that they must die in supernova explosions. Theoretical calculation suggests that stars begin life in a main sequence with roughly 8 to 20 solar masses, will leave behind neutron stars, and stars even more massive than that are formed to form black holes. A question: when are the quizzes written on the study guide take place? That will be after recess. You'll have your first quiz, and that will be online on ClickUp. So how massive can a neutron star be? And that is a critical question and difficult one to answer, because scientists don't know the strength of pure neutron material. They can't make such a matter in the laboratory. So its properties must be predicted theoretically. The most widely accepted calculations suggest that a neutron star cannot be more massive than about 3 solar masses. If a neutron star were more massive than that, the degenerate neutrons would not be able to support weight, and the object would collapse, presumably becoming a black hole. Two of the most massive neutron stars observed have masses of 1.94 and 2.74 solar masses, evidence in favor of that hypothesis. So this is actually quite amazing, because you have a star that's 8 to 20 solar masses in mass, it collapses in on itself, ends up as a neutron star with a solar mass of about 1.94 to about 3 solar masses. Everything, so if you add more mass to it, then it will become a black hole. But that is quite remarkable with the collapse and where it finally stops. So mathematical models predict that a neutron star should be only 10 or so kilometers in radius, which combined with a typical mass means it must have a density of almost 10 to the power 15 grams per cubic centimeter. This is roughly the density of an atomic nucleus. So you can think of neutron star as matter with absolutely all empty space squeezed out of it. On Earth, a sugar cube-sized lump of this material would weigh more than 1 billion tons. So this is just a scale representation or analogy to help us. So if you put a tennis ball in a road map, illustrated the scale of a neutron star. So in this object, in this example, a neutron star will be the size of a tennis ball, and this is the greater Washington, D.C. area. And that's to show how big a neutron star is and how much mass it actually contains. So some physicists, the same physics you have, simple physics, the same physics you have used in previous chapters to understand normal stars, predicts that neutron stars should not be hot, spin rapidly, and have strong magnetic fields. And you have seen that contraction heats the gas in a star. As gas particles fall inward, they pick up speed, and when they collide, the high speeds become thermal energy. The sudden collapse of the core of a massive star to a radius of 10 kilometers should heat it up to 1 trillion degrees. Astronomers calculate that neutron stars should initially cool rapidly from that astonishing high temperature because neutrinos can escape from the entire volume and carry energy away. After a few years, neutron stars will cool down to a mere million degrees or so, and neutrinos won't be produced in bulk. From that point on, neutron stars should cool slowly because the heat can escape only from the surface. And neutron stars are so small, they have little surface from which to radiate. The principle of conservation of angular momentum predicts that neutron stars should spin rapidly. All of the stars rotate because they form from swirling clouds of interstellar matter. And as the star collapses, it must rotate faster because it conserves angular momentum. So if the sun collapsed to a radius of 10 kilometers, its rate of rotation would increase from once every 24.5 days to more than 2,000 times a second. So you might expect the collapse of a core of a massive star to rotate in a range of 10 to 1,000 times per second. It isn't hard to understand how a neutron star could have a powerful magnetic field. All the stars have magnetic fields, and some have fields 1,000 times stronger than the sun's. And the field is frozen into the ionized gas of the star. And when it collapses into a neutron star, the field is squeezed down, concentrated, and made as much as 1 billion times stronger. Theory predicts that properties of neutron stars, but it also predicts that they should be difficult to observe. Neutron stars are very hot. So from your understanding of black body radiation, you can predict that they will radiate most of their energy in the gamma ray and X-ray part of the spectrum. Radiation that could not be observed in the 1940s and 1950s because astronomers could not yet put telescopes above Earth's atmosphere. Also, the small surface areas of neutron stars mean that they will be faint objects. Consequently, astronomers of the mid-20th century were not surprised that none of the newly predicted neutron stars had been found. Neutron stars were at that point entirely theoretical objects. So do you guys know who Professor Jocelyn Bell is? So Jocelyn Bell is a very, very, very important figure in astronomy. And do you guys know why? So when she did her master's and PhD work, she did it at the Cambridge University. And Cambridge University has their own telescope at Jodrell Bank. So what she did is she were observing an object in space, and then this is just a time. So then this is just for illustration purposes. They would realize the object they're detecting pulses at exact time intervals. And they thought, well, where is this signal come from? So there was predictions that it could be aliens, it could be a spy satellite. And then they actually started to realize this, but this is coming from space. So they renamed it LGM for Little Green Men, and they thought it was aliens trying to communicate. But after investigating it, they actually realized this is actually a neutron star. And that is the magnetic field of the pulsar of the neutron star flashing across Earth. So you can think about it as a lighthouse spinning around. And a beam of light is the magnetic field that flashes across Earth. So every time in the stick, the pulse ranged it can range from 0 to 0.033 seconds to 0.75 seconds. But in the case of of Jocelyn Bell, it was very, very stable. And that is the discovery of the first neutron stars. And then neutron stars with the flashing radiation across Earth are called pulsars. So pulsars are a type of neutron star, and that predicted, or it showed that a theory was correct. Something interesting about pulsars is they are very, very, very good at keeping time. So we can use them as very accurate measurements for time. So the most accurate way on Earth we can measure time is atomic clocks. Are you guys familiar with atomic clocks? So an atomic clock is the most accurate way of keeping time. So you get a few variations of them. So to put it in perspective, there are, the last time I checked, 4 atomic clocks in South Africa. Far as I understand, there is 6 atomic clocks on the African continent, and 4 of them is in South Africa. So how it works is it's a vacuum sealed chamber. So you can pump in one molecule of hydrogen, or another one is methanol. So those are the 2 major varieties. Let's take the hydrogen one, for example. Then you give it an electric current, and due to the electric current, the molecule will start oscillating up and down in the vacuum chamber. So once it reaches the one side, 1 second has passed. Once it reaches the other side, another second has passed. And that's usually accurate and stable to roughly 10 to the power minus 15 of a second. So those are very, very, very accurate clocks, and the most accurate time way we can keep time, and we use them for experiments that is time sensitive. So usually any observatory in the world has an atomic clock, sometimes called a maser clock is another word for them as well. But some of these pulsars, the way they are spinning around, are even more stable and more accurate than our atomic clocks on Earth. Some of the pulsars are even accurate to 10 to the power minus 25 of a second, which is very, very, very cool. So a cool place where a neutron star was discovered is in the center of the Crab Nebula. So you can think about a pulsar, like I said, as a lighthouse that flashes energy across Earth. So when we create a model of a pulsar, firstly, a pulsar does not pulse, but rather emits beams of radiation that sweep around the sky as the neutron star rotates. And if the beams do not sweep over Earth, the pulses will not be detectable by Earth's radio telescopes. Secondly, the mechanism that produces the beams involves extremely high energies and is not fully understood. And then lastly, modern space telescopes observing from Earth's atmosphere can image details around young neutron stars and even locate isolated neutron stars whose beams of electromagnetic radiation do not sweep over Earth. So when pulsars first form, it's spinning fast, perhaps 100 times a second. The energy it releases into space comes from its energy of rotation. So as it blasts beams of radiation outwards, its rotation slows. The average pulsar is apparently only a few million years old, and the oldest are about 10 million years old. Presumably older neutron stars rotate too slowly to generate detectable radio beams. You can expect that a young neutron star should emit powerful beams of radiation, and the Crab Nebula is an example. only about 960 years old. The Crab pulsar is so powerful, it runs all across the electromagnetic spectrum at radio, infrared, visible, X-ray, and gamma ray wavelengths. So when we look at a spectra, this is the peak we will see flashing across Earth with the electromagnetic radiation from a pulsar. So when we look at the center of our own galaxy, so here is the Milky Way center, and here we can see the Crab pulsar, here we can see another pulsar, here's the Vela pulsar, and here is a blazar as well. So here we can see the nebula with the pulsar inside, and here we can see the electromagnetic beam of the rotating pulsar beaming outwards. So one thing that's also very interesting is we also get binary pulsars. So nearly 2,000 pulsars are now known, and some are located in binary systems. These pulsars are of special interest because astronomers can learn more about these neutron stars by studying the orbital motions of the binary. Also, in some cases, the mass can flow from the companion star onto the neutron star, and that produces high energy violence. The first binary pulsar was discovered in 1974 when astronomers Joseph Taylor and Russell Hulse noticed that a pulse period of the pulsar PSR was changing. The period first grew longer and then grew shorter in a cycle that took 7.75 hours. Thinking of the Doppler shift seen in spectroscopic binaries, the radio astronomers realized that a pulsar had to be in a binary system with an orbital period of 7.75 hours. So when the orbital motion of the pulsar carries it away from Earth, astronomers see the pulse period lengthen slightly, so redshift. Then when the pulsar rounds its orbit and approaches Earth, they see the pulse period shorten slightly, hence the blue shift. So the resulting graph of radial velocity versus time was then analyzed to find the shape of the pulsar's orbit. An analysis of the PSR pulsar showed that a binary system consists of two neutron stars, one of which is silent, separated by a distance roughly equal to the radius of our sun. So here is the center of mass, here is the one pulsar, and here we can see the radial velocity. So yet another surprise of these binary pulsars is in 1916, Einstein's theory of general relativity described gravity as a curvature of space-time. And Einstein realized that any rapid change in a gravitational field should spread outward at a speed of light as gravitational radiation. Tyler and Hulse were able to show that an orbital period of the binary pulsar is slowly growing shorter because the stars are radiating orbital energy away at exactly the rate expected for gravitational radiation, and so are gradually spiraling toward each other. Normal binary stars are too far apart and orbit too slowly to emit significant gravitational radiation. Taylor and Hulse won the Nobel Prize in 1993 for their work confirming general relativity using binary pulsars. In 2016, it was announced that a Laser Interferometer Gravitational Wave Observatory, its acronym is LIGO, and we talked about LIGO in a previous lecture, had made a first direct detection of gravitational radiation. So dozens of pulsars have been found orbiting stars of various kinds. And by analyzing the Doppler shifts in their pulse periods, astronomers can estimate the masses of the neutron stars. So typical masses are about 1.4 solar masses as predicted by theory. In 2004, radio astronomers announced the discovery of a double pulsar, two pulsars that orbit each other in only 2.4 hours. One spins 44 times a second and the other spins once every 2.8 seconds. The system is a pulsar jackpot because the orbits are nearly edge-on to Earth, and the powerful magnetic fields that are gas trapped in the fields eclipse one another, giving astronomers an opportunity to study the size and structure. Furthermore, the theory of general relativity predicts that these pulsars are emitting gravitational radiation, so that their separation is decreasing by 7 millimeters per year. The two neutron stars will merge in 85 million years, presumably triggering a violent explosion. In the meantime, the steady decrease in orbital period can be measured, giving astronomers another test of general relativity and gravitational radiation. The gravitational fields of neutron stars are so strong that they can be sites of titanic violence. An astronaut stepping into the surface of a neutron star would be instantly smooshed into a layer only 1 atom thick. If you dropped an apple onto the surface of a neutron star from a large distance, it will hit with an impact equivalent of a mega nuclear bomb. In general, a particle falling from a large distance to the surface of a neutron star will release energy equivalent to 0.2 mc squared, where m is the particle's mass at rest and c is the speed of light. So this is how the binary pulsar will look like and how it will see its pulses. So binary pulsars are very interesting to see. But then for the last thing about pulsars and neutron stars we have is also very, very fast pulsars. So of pulsar suggests that newborn pulsars should blink rapidly and old pulsars should blink slowly. In fact, a handful of the fastest may be quite old. So the current fastest known pulsar is catalogued as PSR J1748, and it pulses at 760 times a second and is slowing down only slightly. And a number of other very fast pulsars has been found, and they are generally known as millisecond pulsars because their pulse periods and therefore the periods of rotation are around a millisecond. And so because a pulsar's period is so precise, astronomers can detect tiny variations by comparing their observations with atomic clocks. So when astronomers checked pulsar PSR B1257, they found variations in the period of pulsation, much like those caused by orbital motion of binary pulsar. However, in the case of this pulsar, the variations were much smaller, and when they were interpreted as Doppler shifts, it became evident that a pulsar was being orbited by at least two objects with planet-like masses of 4.1 and 3.8 Earth masses. The gravitational tugs of these planets made the pulsars wobble about the centers of mass of the system by no more than 800 kilometers, producing the observed tiny changes in their period. So here we can see that little wobble caused by the planets orbiting the pulsar. So, ladies and gentlemen, what is this? Yes, that's a black hole, the first image. So before we start, let's look at a quick video of black.
As we've seen over the past few episodes, a lot of really epic stuff happens when a star dies. If the star's core is less than 1.4 times the mass of the sun, it becomes a white dwarf, a very hot ball of super compressed matter about the size of the Earth. If the core is heftier, between 1.4 and 2.8 times the sun's mass, it collapses even further, becoming a neutron star that's only 20 kilometers across. The neutron soup inside of it resists the collapse and prevents the core from shrinking anymore. But what if the mass is more than 2.8 times the sun's? If that happens, the gravity of the core can actually overcome the tremendous resistance of the neutrons and continue its collapse. What force can possibly stop it now? It turns out none. None more force. There is literally nothing in the universe that can stop the collapse. The core of the star is about to go bye-bye. Way back in episode 7, I talked about escape velocity, and it's about to become a major player in the unfolding events of the collapsing core of a high-mass star. In brief, it's the velocity at which you need to fling something off the surface of an object to get it to escape. For the Earth, the escape velocity is about 11 kilometers per second. Get something moving that quickly, and it's gone. It'll never fall back. The Sun, which has much stronger gravity than Earth, has an escape velocity of over 600 kilometers per second. A neutron star, with its immense gravity, can have an escape velocity of 150,000 kilometers per second. That's half the speed of light. Keep that in mind, and let's go back to the collapsing core of the star. As it shrinks, its gravity gets stronger and stronger. That means its escape velocity gets higher and higher. When it's neutron star size, the escape velocity is half the speed of light. But if it's more than 2.8 times the mass of the sun, the core will keep collapsing. When its size drops just a little bit more, down to roughly 18 kilometers, an amazing thing happens. The escape velocity at its surface is equal to the speed of light. And, well, that's a problem, because in our universe, nothing can travel faster than the speed of light. Not a rock, not a rocket, not even light itself. Once the core of the star shrinks down smaller than that magic size, nothing can escape. No matter can come out, so it's like an infinitely deep hole. And no light can come out, so it's black. We should come up with a snappy name for such an object. A black hole is the ultimate end state for the core of a high-mass star. Whatever happens in a black hole stays in a black hole. That region of space, that surface around the black hole where the escape velocity is the speed of light, is called the event horizon. For that reason, any event that happens inside can't be known. It's beyond the horizon for us. Black holes mess with our concepts of space and time. The math and physics of black holes is incredibly complex, so much so that even after several decades of study, physicists still argue over a lot of their properties. This has led to a lot of misconceptions about them too. All right, let's get this out of the way right now. The sun cannot become a black hole. It takes a stellar core at least about 3 times the mass of the sun to overcome neutron degeneracy pressure. That means the original star must have something like 20 times the sun's mass or more. So we're safe from that particular sci-fi scenario. Here's another misconception. A lot of people think of black holes as cosmic vacuum cleaners, sucking in everything near them. But that's not really true. They have powerful gravity, yeah, but only when you're very close to one. The power of a black hole comes from its mass, certainly, but just as important is its size, or really, its lack of size. If you could turn the sun into a black hole, which you can't, but let's pretend you could, then the Earth would orbit it pretty much exactly as it does now. From 150 million kilometers away, the Earth doesn't care if the sun is big or tiny. We're so far away that it doesn't matter. It gets to be a big deal when you get close. Remember from episode 7 about gravity, the strength of gravity you feel from an object depends on how massive it is and your distance from its center. The closest you can get to the sun is by touching it, being on its surface, about 700,000 kilometers from its center. If you get any closer to its center, you're inside it. The material outside of your position is no longer pulling you down, and so the gravity you feel will actually decrease. But if the sun were crushed down to about 6 kilometers across, it would be a black hole. You could get much closer than 700,000 kilometers to it, and as you did, you'd feel a stronger and stronger pull as you approached it. So, from far away, a black hole with, say, 10 times the sun's mass would pull on you just as hard as that same mass. You can orbit a black hole too, as long as you keep a safe distance between you and it. Orbiting a 10 solar mass black hole would be just like orbiting a 10 solar mass star, except not so hot and bright. Black holes are weird enough without the misconceptions. Black holes also come in different sizes. The kind of black holes I've been talking about have a minimum mass of about 3 times the sun's, and might get as high as a dozen or more times the sun's mass. if the parent star was big enough. We call these stellar mass black holes. If it happens to gobble down more matter, it gets more massive, and the event horizon grows as well. The black hole gets bigger. The idea that huge black holes could form in the centers of galaxies was first proposed in the 1970s, and it wasn't much later that the first one was found in the center of our own Milky Way galaxy. We've measured its mass at a whopping 4.3 million times the sun's mass. And now we think every major galaxy has one at its heart too, and in fact may be crucial in the formation of galaxies themselves. I'll discuss those more in a future episode. Here's a fun thought. What would happen if you fell into one, say a stellar black hole with 10 times the sun's mass? You'd die. But what happens in the few milliseconds before you leave the known universe forever is actually pretty interesting. As we've seen many times in our own solar system, tides are important. They arise because gravity weakens with distance. So a big object like a moon gets stretched by its planet's gravity. The far side of the moon is pulled less than the near side. A black hole has incredibly intense gravity, so the tides it can inflict are serious indeed. They're so strong that if you fell into a stellar mass black hole feet first, the force of gravity on your feet can be millions of times stronger than the force on your head. Remember, even the meager tides of a planet can rip moons apart. When you multiply that force by 1,000,000, you're in trouble. As you fall in, your feet are pulled so much harder than your head that you stretch, pulled like taffy. You'd become a long, thin noodle, kilometers in length, but narrower than a hair wide. Astronomers call this, and no, I'm not kidding, spaghettification. This would happen pretty close to the black hole, just a few dozen kilometers out. If you fell in from a long distance, you'd be moving pretty near the speed of light by that point, and you'd only have a millisecond or so before it killed you anyway, so yay? Note that this is only for stellar mass black holes. Supermassive black holes are far bigger, millions or billions of kilometers across. Compared to that size, the distance between your head and feet is small, so the tides across you aren't nearly as severe. You'd fall in pretty much intact, if that makes you feel any better. But compared to either flavor of black hole, a star still has substantial size, and one that gets too close to any black hole can be disrupted via tides. In March 2011, astronomers witnessed just such an event. In a distant galaxy, a star apparently got too close to a black hole and was torn apart by the ferocious tides. As the star was disrupted, it flared into brightness, momentarily blasting out 1 trillion times the sun's energy. That's how we were able to see it, even though it was several billion light years away. But I've saved the weirdest thing for last. One of Albert Einstein's biggest ideas is that space isn't just emptiness. It's an actual thing, like a fabric in which all matter and energy is embedded. What we perceive as gravity is really just a warping of this space, like the way a bowling ball on top of a bed warps the shape of the mattress. The more massive an object, the more it warps space. Not only that, but space and time are basically two parts of the same thing, what we now call space-time. You can't affect one without affecting the other. Einstein calculated that when a massive object warps space, it also warps time. Someone deep inside the gravitational influence of an object perceives time as ticking more slowly than someone far away from that object. I know, it's bizarre. We think of time as just flowing, and everyone should see it move at the same rate. But the universe is under no obligation to obey our preconceptions. Einstein was right. He was right a lot. This slowing of time is stronger the stronger the gravity of the object is. So your clock ticks a bit slower than someone far away from Earth, for example. The effect is tiny but real, and we've actually measured it on Earth with extremely precise clocks. However, if you get near a black hole, the effect gets a lot stronger. In fact, black holes warp space-time so much that at the event horizon, time essentially stops. You'd see your clock running normally and you'd just fall in, bloop, gone. But someone far away would see your clock ticking more slowly as you fell in. And this isn't a mechanical or perception effect. It's actually woven into the fabric of space. To someone outside looking down on you, your fall would literally take forever. But then they wouldn't be able to actually see you. The light you emit would have to fight the intense gravity of the black hole to get out. And to do that, it would lose energy. This is very similar to the Doppler redshift I've talked about in earlier episodes, and it's called a gravitational redshift. When you're right at the event horizon, just when an outside observer would see your clock stop, they'd also see the light coming from you infinitely redshift. Your light would lose all its energy trying to leave the vicinity of the black hole, and you'd be invisible. And from your viewpoint, buckle up, because this is wow. You'd see the universe speed up, And just as you hit the event horizon, all of time would pass. All of it. And all that light coming at you from the universe would be blue shifted, becoming such high energy that you'd be fried. But since you're about to fall into a black hole, you probably wouldn't care. See? Like I said. Wow. Black holes are so strange, with such fiercely complicated math and physics to explain them, that scientists are still trying to figure out even basic things about them. For example, some scientists argue that the event horizon as we understand it may not actually exist, and that when you apply quantum mechanics to black hole physics, you find particles can slowly leak out. We're still new at this and struggling to understand what may be the most complex objects in the cosmos. Black holes, as bizarre and counterintuitive as they are, keep popping up from here on out as we poke our noses into more and bigger astronomical objects. While they may seem scary and weird, and let's be honest, they are, they have literally shaped most of the objects we see in the universe. Today you learn that stellar mass black holes form when a very massive star
So that is really cool, and it provides us with an overview of what black holes is about. So let's go back to our slides. So we have now done the path from a supernova to a neutron star. Now we need to talk about a supernova to a black hole. So where does the idea of a black hole comes from? So the English astronomer John Michell proposed in 1784 that such an object could exist. And he predicted it by simplistic calculations he made. And he calculated that such an object would need to exceed the sun's size by a factor of 500, and that a surface escape velocity exceeds the speed of light. But then in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influenced the motion of light. So in 1905, Albert Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. And this was the theory of special relativity. It introduced a new framework of all of physics and proposed new concepts of space and time. Einstein then spent 10 years trying to include acceleration in the theory and published his theory of general relativity in 1915. In it, he determined that massive objects cause a distortion in space-time, which is felt as gravity. So, on a side note, you guys know for what Albert Einstein won the Nobel Prize in Physics for? Yes, for the photoelectric effect. So Einstein is more popularly known for his theory of general and special relativity, but he actually won the Nobel Prize in Physics for the photoelectric effect. So in the theory of general relativity, Einstein published the Einstein field equations that he created, but he had no solution for the field equation. So you don't need to know the field equation. This is just background information. So something interesting as part of the background information and general relativity, where does mc squared comes from? So when you start off by integrating kinetic energy, so you have kinetic energy over the line integral f dot ds, where f is the force in the direction of displacement ds and s is distance over the force x. So if we can define with Newton's second law of motion that we can plug into the equation, then becomes this. And then we can start integrating it. So note that the velocity limit c, the speed of light, and at c, time dilation becomes 100%. So now we can integrate by parts. So now we do integration by parts, and then by integration by parts, we have our end and our beginning. So kinetic energy at the end, kinetic energy at the beginning. Kinetic energy at the beginning falls away because that is 0, and then we are left with E equals mc squared. So this is just a really cool derivation. So no need to know this. This is just for background information. So after Einstein has published these equations, so more specifically his field equation, Karl Schwarzschild found the solution to the field equations, which described the gravitational field of a point mass and a spherical mass. And a few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently achieved the same result for a point mass. So this is the field equations and what each of the terms mean. So you don't need to know this, as this is just background information. So Schwarzschild predicted that you would have a point mass that has the same characteristics as a black hole. But then we have this guy, Stephen Hawking, and he provided a more mathematical understanding of black holes, and that is what his life work is about. So you're all familiar with the Event Horizon Telescope. So the Event Horizon Telescope is a network of telescopes. Which is important about these telescopes is they all can observe X-rays, so frequencies at X-rays, and there's not many of them around the globe because X-rays get absorbed by the water vapor in our atmosphere. So those telescopes needs to be at places that's extremely dry, or in places that's extremely high above sea level, so you are above the water vapor line. So all these telescopes can observe X-rays. Something interesting is one is Antarctica. So do you guys actually know that Antarctica is the biggest desert in the world? Awesome. So now you can network all these telescopes, and by making use of fancy math called interferometry, you can set up a very long baseline interferometry, and then you can make a virtual telescope that is the size of the distances between these telescopes, providing a very large telescope that's very sensitive to observe a black hole with. So in the 1970s, this is what they imagined a black hole would look like. But while the Event Horizon Telescope was observing a black hole, they also created mathematical models of what the first image of a black hole might look like. So this is the first image or the simulation. So here in the middle, we call that the shadow of the black hole. So we cannot see anything in it. So this is literally looking into a black hole. This is the event horizon around it. So we've learned that event horizon is the point of no return. If you're outside event horizon, you can still escape the gravitational pull. If you're inside a black hole, the event horizon, you can't. We've also learned about accretion disks. So when matter is falling into a black hole, it doesn't fall in directly. It falls in a accretion disk spinning around the black hole. And you have molecules rubbing against one another, creating thermal energy, and that creates X-rays. So the brighter the colors here, the more X-rays that is being released. So how do you think the first recorded image compares to the simulated image? This is the first image. So the first image is spot on to what the simulated image predicted, meaning we understand the physics to a black hole. So we understand the physics up until the event horizon, but our understanding of what happens inside the event horizon breaks down. Are you guys familiar with the term event horizon? Ag nie ben toe rise nie, escape velocity. So escape velocity is the velocity you need to escape the gravitational pull of a certain object. So if you launch a rocket, what the escape velocity needs to be. So here is the formula. You only need to know this for background information, but here using this equation, we can calculate the escape velocity of what we need for a certain object to escape the gravitational pull of Earth. So question, so does everything in space have to orbit something else? Get orbited by other objects? Are there any objects in space that have nothing orbiting them and do not orbit anything and are just floating completely stationary? Yes, that happens. So in sort of that happens. So usually all objects is in some sort of galaxy. And everything in a galaxy orbits around their central black hole. So what we will learn in later chapters, every galaxy contains a supermassive black hole in the center. And that's what's keeping the galaxy together. But outside of our own galaxy, there's not any objects floating around. So yes, you can have objects on their own, for example, in a solar system, not a solar system, in a galaxy, but they will always orbit around the center of our galaxy. So your answer is yes and no, if that makes sense. Awesome. So those of you that watched SpaceX videos, they're usually aiming for about 27,000 kilometers per hour. And that is the escape velocity of their rocket. So if you could make an object massive enough or small enough, its escape velocity could be greater than the speed of light. Albert Einstein's theory of special relativity, published in 1905, says nothing can travel faster than the speed of light. So even photons, which have no mass, would be unable to escape. And such a compact, massive object could never be seen because light could not leave it. Long before Einstein's relativity, the Reverend John Michell, a British gentleman astronomer, realized this particular consequence of Newton's law of gravity and motion. And in 1783, he pointed out that an object of 500 times the radius of the sun, but of the same density, would have an escape velocity greater than the speed of light. Then all that emitted from such a body would make it return towards it. So Michell didn't know, but he was talking about a black hole. So if the core of a star contains more than 3 solar masses when it collapses, no force can stop it. So remember, we learned a neutron star, when the core collapses, the final core just stops before 3 solar masses. But if the collapsed core contains more than 3 solar masses when it collapses, no force can stop it. It cannot stop collapsing when it reaches a density of a white dwarf, because degenerate electrons cannot support that weight. And it cannot stop when it reaches the density of a neutron star, because not even degenerate neutrons can support that weight. So no force remains to stop the object from collapsing to 0 radius. As an object collapses, its density and the strength of its surface gravity increase. If an object collapses to 0 radius, its density and gravity become infinite. Mathematicians call such a point a singularity. But in physical terms, it is difficult to imagine an object of 0 radius. And some theorists believe that a singularity is impossible, and that the laws of quantum physics must somehow hold the collapse of a radius to roughly 10 to the power 20 times smaller than a proton. So astronomically, it seems to make little difference. If the contracting core of a star becomes small enough, the escape velocity in that region of the space around it is so large that no light can escape. And this means you can receive no information about an object or about the region of space near it. Because it emits no light, such a region is called a black hole. If the core of an exploding star collapsed into a black hole, the expanding outer layers of the star could produce a supernova remnant. But a core would vanish without a trace. In 1916, Albert Einstein published a mathematical theory of space and time that became known as the general theory of relativity. And Einstein treated space and time as a single entity called spacetime. His equations showed that gravity could be described as a curvature of spacetime. And almost immediately, the astronomer Karl Schwarzschild found a way to solve Einstein's equations to describe the gravitational field around a single non-rotating electrically neutral lump of matter. That solution contained the first general relativistic description of a black hole. And non-rotating electrically neutral black holes are now known as Schwarzschild black holes. So that is something to know. I can ask, for example, in the exam, what is a Schwarzschild black hole? In recent decades, theorists such as Roy Kerr and Stephen Hawking have found ways to apply the sophisticated mathematical equations of general relativity, electromagnetism, and quantum mechanics to describe charged rotating black holes. For this discussion, the differences are minor, and you may proceed if all black holes were Schwarzschild black holes. So Schwarzschild's solution shows that if matter is packed into a small enough volume, then space-time curves back on itself. And objects can follow paths that lead into the black hole, but no path leads out. So nothing can escape. Because not even light can escape, the inside of the black hole is totally beyond the view of an outside observer. The event horizon is the boundary between that isolated volume of space-time and the rest of the universe. And the radius of the event horizon is called the Schwarzschild radius, or RS in short. So a collapsing stellar core must shrink inside the Schwarzschild radius to become a black hole. Although the Schwarzschild's work was highly mathematical, his conclusion is quite simple. The Schwarzschild radius depends only on the mass of the object. In this formula, g is the gravitational constant, m is the mass in kilograms, and c the speed of light in meters per second. A bit of arithmetic shows that a 1 solar mass black hole has a Schwarzschild radius of 3 kilometers, and a 10 solar mass black hole has a Schwarzschild radius of 30 kilometers, and so on. And every object has a Schwarzschild radius determined by its mass, but not every object is a black hole. For example, Earth has a Schwarzschild radius of about 1 centimeter, meaning that it could become a black hole if you squeezed it smaller than 1 centimeter radius. It is a common misconception to think of black holes as giant vacuum cleaners that will eventually suck in everything in the universe. A black hole is just a gravitational field, and at a large enough distance, its gravity is no greater than that of normal objects of similar mass. So if the Sun were replaced by 1 solar mass black hole, the orbits of the planets would not change at all. So this figure illustrates this by representing gravitational fields as curvature of the fabric of space-time, and normal uncurved spacetime is represented by a flat plane, and the presence of a mass such as a star curves the plane to produce a depression. The extreme curvature around a black hole produces a deep funnel-shaped surface in this graphic representation. So you can see from the graphs that the gravity of a black hole becomes extreme only when you approach close to it. Now we can check off another common misconception that may strike you as silly because of special effects in movies and TV. Some people think black holes should actually look like funnels. Of course, the graphs of the strength of gravity around black holes look like funnels. But the black holes themselves are not shaped like funnels. If you could approach a black hole, You might be able to see hot gas swirling inward, but you wouldn't be able to see the black hole itself. Before you can search for real black holes, you need to understand what theory predicts about a black hole. To explore that idea, you can imagine leaping feet first into a Schwarzschild black hole. If you were to leap into a black hole of a few solar masses from a distance of 1 AU, the gravitational pull will not be very large, and you would fall slowly at first. Of course, the longer you fell and the closer you came to the center, the faster you would travel. Your wristwatch would tell you that you fell for about 2 months by the time you reached the event horizon. Your friends who stayed behind would see something different. They would see you falling more and more slowly as you came closer to the event horizon, because, as explained by general relativity, time slows down in curved space-time. This is known as time dilation. In fact, your friends would never actually see you cross the event horizon. To them, you would fall more and more slowly until you seemed hardly to move. Generations later, your descendants could focus their telescopes on you and see you still inching closer to the event horizon. You, however, would have sensed no slowdown and would conclude that you had reached the event horizon after about 2 months. Another relativistic effect would make it difficult to see you with normal telescopes. As light travels out of gravitational field, it loses energy, and its wavelength grows longer. This is known as the gravitational redshift. As you fell toward a black hole, your friends would need to observe at longer and longer wavelengths to detect you. While these relativistic effects seem merely peculiar, other effects would be quite unpleasant. If you were falling feet first, you would feel your feet, which would be closer to the black hole, being pulled in more strongly than your head. This tidal force, and at first it would be minor, but as you got closer to the black hole, the tidal force would become very large. Another tidal force would compress you as both your left and your right side fell towards the center of the black hole. For any black hole with a mass like that of a star, the tidal forces would crush you sideways and stretch you lengthwise, long before you reach the event horizon. So this is just a graphic representation of what the spaghettification would look like. So the friction from such a severe distortions of your body would heat you to millions of degrees, and you would emit X-rays and gamma rays. Some people have suggested that it is possible to travel through the universe by jumping into a black hole in one place and popping out another somewhere far across space. That might make good for science fiction, but tidal forces would make it an unpopular form of transportation, even if it worked. You now know how to find a black hole. X-rays, it may be a black hole into which matter is falling and being heated. The first X-ray telescopes reached orbit in the 1970s, and that allowed astronomers to begin searching for evidence of black holes. They tried to find one or more objects that were obviously black holes, and that very difficult search is a good illustration of how the unwritten rules of science help scientists understand nature. A black hole alone is totally invisible because nothing can escape from its event horizon. But if matter flows into a black hole, it will whirl through an accretion disk and become hot enough to emit X-rays before it reaches the event horizon. An isolated black hole in space will not have much matter flowing into it, but a black hole in a binary system might receive a steadily flow of matter transfer from the companion star. And this suggests you can search for black holes by looking closely at X-ray binaries. So some X-ray binaries, such as Hercules X1, contain a neutron star, and they will emit X-rays much as would a binary containing a black hole. And you can tell the difference in two ways. If the compact object emits pulses, you know there's a neutron star because the neutron star has a solid body within which powerful magnetic fields are generated. And as the neutron star rotates, the magnetic field emits beams that sweep around the sky, producing pulses as they pass across Earth. A black hole inside its event horizon cannot emit regular pulses like those from a neutron star. Another clue depends on the mass of the object. If the mass of the compact object is greater than about 3 solar masses, it cannot be a neutron star, it must be a black hole. The first X-ray binary suspected of harboring a black hole was Cygnus X1, the first X-ray object discovered in the constellation Cygnus. It contained a supergiant star of spectral type B0, and a compact object orbiting each other with a period of 5.6 days. Astronomers suspected that the X-rays were emitted by matter from the star flowing into the compact object. That object is invisible, but Doppler shifts in the spectrum reveal the motion of the B0 star around the center of mass of the binary. From the geometry of the orbit, astronomers were able to calculate that the mass of the compact object had to be greater than 3.8 solar masses, well above the maximum for a neutron star. To confirm that black holes exist, astronomers needed a conclusive example, an object that couldn't be anything else. And Cygnus X1 didn't quite pass the test when it was first discovered. Perhaps the B supergiant was not a normal supergiant, and its portion of the system mass was incorrectly estimated, or perhaps the system contained a third star. Either possibility would distort the analysis. At the time, astronomers could not conclusively show that Cygnus X1 contained a black hole. It took years of work to understand Cygnus X1. Further observations and analysis show that a B0 star has a mass of about 25 solar masses, and a compact object is about 10 times the mass of the Sun. Astronomers conclude that matter flows from B0 star as a long stellar wind, and much of that matter gets caught in a hot accretion disk about 5 times larger in diameter than the orbit of Earth's moon. And the interior, in a few hundred kilometers of the disk, have a temperature of about 2 million Kelvin, hot enough to radiate X-rays. So this is just an artist's representation of how this system Cygnus X1 looks like. So here we can see for the black hole, we can see the object, what type of star it is, the orbital period, and the mass of the black hole in this binary system. So another way to confirm that black holes are real is to search for evidence of their distinguishing characteristics, so the event horizons, and that search has also been successful. So matter flowing, so now talking about compact objects with disks and jets. So matter flowing onto a neutron star or onto a black hole forms an accretion disk. And that can produce some surprising phenomena, and astronomers are just beginning to understand these peculiar effects. Observations show that some compact objects are emitting jets of gas and radiation in opposite directions, and these jets are similar to the bipolar outflows ejected by protostars, but much more powerful. The Cold War played a minor part in the story of neutron stars and black holes. In 1963, a nuclear test ban treaty was signed, and by 1968, the United States was able to put a series of satellites in orbit to watch for nuclear tests that were violations of the treaty. A nuclear detonation emits gamma rays, so these satellites were designed to watch for bursts of gamma rays coming from Earth. The experts were startled when the satellites detected about 1 gamma ray burst a day coming from space. And when those data were finally declassified in 1973, astronomers realized that the bursts might be coming from neutron stars and black holes. And these bursts are known as gamma ray bursts, or abbreviated GRBs. So this is a gamma ray detection from satellites. So gamma ray bursts are hard to study because they occur without warning and fade quickly. But starting in 1997, new satellites were put into orbit to detect gamma ray bursts. Their data show that there are two kinds of gamma ray bursts. Short bursts last less than 2 seconds, but longer bursts can go on for tens of seconds, up to several minutes. Specialized space observatories now can detect bursts quickly, determine their location in the sky, and immediately alert astronomers on the ground. So when telescopes on Earth swivel to image the locations of the bursts, they're detecting fading glows that resembled supernovae. Stellar interior models indicate that a star more massive than some upper limit of about 20 solar masses can exhaust its nuclear field and collapse directly into a black hole. Models showed that a collapsing star would conserve angular momentum and spin very rapidly, slowing the collapse of the equatorial parts of the star. The poles of the star would fall in quickly, and that would focus beams of intense radiation and eject gas that would blast out along the axis of rotation. And such an eruption has been called a hypernovae. So this is the representation of a hypernova. So the collapse of the core of a massive star begins along its axis of rotation because the rotation of the star slows the collapse of the equatorial regions. And then within seconds, the remaining portions of the core falls in. And beams of gas and radiation strike surrounding gas and generate beams of gamma rays along the rotation axis. And then the gamma ray bursts fades in seconds, and hot accretion disk is left around the black hole. Short gamma ray bursts, on the other hand, don't seem to be associated with hypernovae. Some repeat, and these repeating bursts seem to be produced by neutron stars with magnetic fields 100 times stronger than that in a normal neutron star, dubbed magnetars. These objects can produce bursts of gamma rays when shifts in magnetic field break the crust of the neutron stars, causing starquakes, and release large amounts of energy. Not all short gamma ray bursts are produced by magnetars. Some bursts have occurred in parts of distant galaxies, where you would not expect to find the young massive stars that produce magnetars or hypernovae. In the afterglows don't resemble fading supernovae. These bursts may be produced by the merger of two neutron stars or neutron star and a black hole that orbited each other. Radiated orbital energy is gravitational radiation and spiraled into each other. Such a collision would cause a violent explosion as the two objects merge to form a new, larger black hole. The gamma ray burst and fading afterglow from neutron star plus black hole merger would be different from that produced by the merger of two neutron stars. Good gamma ray bursts occur near Earth, and the nearest known binary pulsar is only about 3,000 light years from Earth. If gamma ray bursts occurred at that distance, the gamma ray would shower Earth with radiation equivalent to a 10,000 megaton nuclear blast, comparable to full-scale nuclear war between superpowers. So the largest single bombs ever made released less than 100 megatons of energy. The gamma rays could create enough nitric oxide in the atmosphere to produce intense acid rain, and also would destroy the ozone layer, exposing life on Earth to deadly levels of solar ultraviolet radiation. Gamma ray bursts can occur relatively near Earth as often as every few 100 million years, and could be one of the causes of the mass extinction that showed up in the fossil records. So, do you guys know this telescope? This is the NEST telescope in Namibia, and its primary mission and objective is to study gamma ray bursts. So if you're ever in Namibia, that's also an awesome site to visit. So when we look at a black hole, these are just the different features described of the black hole. So this was tweeted by Professor Brian Greene when the first black hole was imaged. It is hard to express how utterly remarkable and astonishingly delightful it is that mathematical scribblings can predict something as bizarre as a black hole. And then looking at the skies with sufficient digits, we find them. And this is the equations of John Mitchell. Neil deGrasse Tyson tweeted, "Scientist, we've produced the first ever image of a supermassive black hole 55 million light years away." In response is, "Ooh, scientist, we have concluded that humans are catastrophically warming Earth." And the response is, "That conflicts with what I want to be true, so it must be false." Bill Nye tweeted, "How can we see a star that gives us no light of its own? Take a look." And that, ladies and gentlemen, is today's lecture. Do you have any questions? No questions. So far as I understand, next week is recess, right? So can you briefly explain how the equation predicts a black hole? Because I presume that equation doesn't churn out the words a black hole probably exists. No, it doesn't. So it's just background information. So the only thing that that equation predicts is it shows that when you compress an object into a point mass, its gravitational effects will go to infinity. And that is basically what the equation shows. And kind of that is what in the 1700s John Mitchell didn't know, is that was actually the black hole that he predicted by doing basic calculus. So I hope that answers your question. So the gamma ray bursts that were detected by 2008, were they that strong cause harm? So yes, they were that strong, but luckily they didn't hit Earth fully directly on. So that was more against the angle, and that's why we were safe on Earth from those. Another question, is the escape velocity of a black hole half the velocity of the speed of light? So if so, why is light not able to escape the black hole? So that means the velocity of a black hole is faster than the speed of light. So you would actually need to travel faster than the speed of light. So that is why nothing cannot escape the gravitational pull of a black hole. And that is why light cannot escape it as well. So another question, server question about assignment on the scale part. Can I email you? Yes, you are more than welcome to email me. So if I'm correct, next week is next week is recess. So I will upload your semester test marks hopefully by the end of the weekend. And then the first class we will have after recess, I will give you back your semester tests. So if you have no further question, sir, I've been waiting to do my observations for the project over the last month, but we haven't had 10 days of cloudy weather. What can we do? Can we use the app you showed earlier in the year? Yes, you can use the app. Let's check what the weather actually is looking like next week. Let me open up weather. So it seems like the weather will start to clear up from around about Thursday. So then you can try and do observations again. But otherwise, you can use resources such as the app to help you. So the app's name is Stellarium. So I'll type it in the chat. So I just want to check if you've seen my emails. Would appreciate your assistance. Is that the emails regarding the semester, the SIG test? Yes, I will reply to that email. So the SIG test will probably, I'm just waiting to get confirmation on the date, but that will most likely be the week after recess, but I will make announcements. So if we use Stellarium, we just take screenshots of the moon once a day at the same time. So technically for the assignment, I don't want Stellarium screenshots. So that means you have to interpret the data and make a drawing of where the sun should have been. The sun's where the moon should have been. If that makes sense. Awesome. So if there's no further questions, I'm also going to log off. So have a wonderful evening. Good luck the rest of the week. Enjoy recess, and I'll see you after recess.